So, can anybody see my presentation?
Yes, thanks.
Excellent. Okay. You know, I'm a theoretician. Sorry, guys. Everything that has more than 2 buttons for me is a real problem. Okay. So I choose that long and winding title for that talk because, I mean, there's a message coming with it. And I think something we can discuss later on, and maybe people will up in is whether we develop our own technologies or we try to improve technologies which are already available in order to battle things like load shedding and other stuff we're all suffering at the moment. Okay, so I found a nice introduction to the topic, which comes from Thomas Edison, believe it or not. And I just read the first sentence: I put my money on the sun and solar energy. Okay, so I will give you some motivation for it. I tell you what's going on at WITS, and the next speaker after me will be my PhD student, co-supervision with Professor Wamwangi Sandile. So I rely a little bit on him giving you the research details, and I will be more general in my talk. So here's the people involved. So in particular at WITS, there's a couple of PhD and MSc students. Sandile's work will feature later on. There's also Francis Otieno, a former postdoc at WITS, and now he has a faculty position in Kenya. So he's again with us, luckily. A long-term PI is Robert Warmbier, especially a lot of what I say about the theory is also his work. And there are a couple of international collaborators in Italy and Germany. Both of them are already retired, so tells you that I'm also the next in line, probably. Okay, so there's a lot more topics on this slide than I actually talk about, so I will be very brief. But I will give you some introduction to augmented photovoltaics and talk about my own specialty, which are solar cell simulations. And so let's kick off right away. So the solar in principle is a simple device. It's based on the photo effect, good old Einstein. And that basically light comes in, creates electron-hole pairs. But in order for this to produce a current, you need a mechanism to separate charge carriers. So in a conventional p-n junction, it's just the changes in the conductivity. So for an electron, has a high conductivity on the n side and a very low conductivity on the p side. So the system sorts itself out in a natural way. As light comes in and creates this extra charge carriers, it drives the system out of equilibrium. So what's happening is that the system wants to go back to equilibrium. It does it by pushing the excess charge carriers out of the system, and luckily we have current, and that's all we want. Yeah. So the efficiencies, you see, state of the art is around 45%, but these are experimental cells. Commercially, we are around 20% with silicon. Organic solar cells, I will show you an example. Fall short in this regard. We're seeing something between 1.5 and 2.5%. Okay, so with every solar cell come a lot of losses, and so one of the losses I want to show you how to mitigate them, or a strategy. It's not working as we expected yet, but I mean that's work in progress. But you have losses, for example, come from the fact that you have photons which have a very low energy. So they cannot be absorbed by the semiconductor, infrared and stuff like that. The other one is some photons have too much energy, and so they lose that energy by thermalization. So what happens is the charge carrier crawls down to the, for example, the electron crawls down to the bottom of the conduction band and gives up energy to the lattice over electron-phonon interaction, and that heats up the solar cell and leads to other types of losses. So So you would like to extract them right away and not lose this energy in thermalization. And you can see it's a large fraction of the solar spectrum that we lose by thermalization. There are other losses intrinsic at the contacts, traps, dislocations, all kinds of stuff. Sorry, but solids are dirty. You can do nothing about that, okay? So our strategy was to take a conventional solar cell and say, maybe we can do some kind of light management with it. And the light management is very simple. There are two strategies. One is to use plasmonic nanoparticles, like little nano antenna, and have them re-radiate the light towards the active center of the solar cell. So Zandile will talk about that later on. And the other one is to take, for example, infrared photons and combine them, and we call that upconversion. And if we use rare earth ions and other systems, out comes a photon which is closer related to the band gap of the semiconductor. So we're actually using infrared light by that way. Or if we have photons which have too much energy, we just split them in two photons which are more closer in energy to the band gap, so we avoid the thermalization losses. So that in a nutshell is what we call augmented solar cells. We use standard technologies and we try to fiddle around with them with nice gimmicks to actually get a better hold on the photons and the charge carriers in the system. So for those of you who are interested and want to read more about this, is a long book chapter we wrote years ago, and here's the reference. So let me just talk about photons and make a more suitable photon out of it, or just cutting the energy of very high energetic photons. So this is work by Francis. Again, organic solar cell is basically a blend of one material likes to take up the electrons, the other material likes to take up the holes. So this is your charge separation mechanism. So what we wanted to do here is use terbium, one of these rare earth ions in zinc oxide. It's the work of Francis. Very nice work here with a very conventional organic solar cell. And so we put that extra layer into the solar cell with the rare earth ions. And what you see here just at the bottom table, obviously there's an improvement in the efficiency that comes from the frequency conversion here. So it's a nice proof of principle, and it appeared in a very respectable journal. So it tells us we are on a good way, but there's still a lot of work to be done. To give you a little bit of background as a theorist, how we go about it. So at electronic levels in a rare earth ion are very complicated, and you're usually only interested in one transition like this one here. So all of these complicated mechanisms are described by rate equations. So what we can do is we solve this rate equation in a steady state. We pump it with light. Normally these systems are pumped by lasers, but we pump it with the solar spectrum. And then we calculate the population density for that particular transition that we are interested in, which I show here in red. So once you have that, you can calculate the corresponding photon flux, then you can calculate the spectral density, and then you can calculate the generation rates of free charge carrier in your system. So we did that. This was our work right at the beginning, and you can see this is a solar cell simulation. You see clear improvements for up and down conversion. The black curve is without up and down conversion, and the green and the red curve are with up and down conversion. So that confirms also what Francis was measuring and what we see on a day-to-day basis with our work here at WITS. Okay, so how did we do this simulation? So that brings me back to the concept of solar cell simulations. So this is basically a typical PN junction. So you have a couple of mechanisms you have to cater for if you want to simulate the process. So first is the generation of electrons and holes in the space charge region or depletion region. So this is where the charge carriers are generated. The next problem is the transport. You know, somehow these charge carriers have to go to the contacts where they are extracted. And the third problem is the extraction at the contacts themselves, okay? So what you do is a lot of equations here. I just tell you the basic physics. So you have three things to cater about. You need the density of the free charge carriers that you have to determine, and you need a voltage across the solar cell. To this end, you have three equations: the Poisson equation and the continuity equations for the currents, which have generations and recombination rates. So what you are seeing here in pink, this is something which Robert Warmby and myself wrote in a long article. These are all entities which are essential for your simulations, but you can take them from first principles density function calculation. So what we showed in a paper which was actually very popular, you can in principle run the simulation of your solar cell entirely on a computer. You don't have to go to the lab. On the other hand, with the simulations, we can tell also the experimentalists what are the ideal values, what you should get as a mobility or as a lifetime. And so they have a guiding line when they're measuring that they're actually in the right range of values. So as you see, the generation rate is at the bottom, and it's rather complicated. It has Phi as the photon flux, that's the incoming intensity from the sun, and this is basically absorbed and gives rise to electron-hole pairs. So you can see at the top is an equation here for the intensity. It changes as you go further or deeper inside the solar cell. So you're losing intensity as you're going deeper into the solar cell. This is the famous Lambert law, yeah, and it describes the absorption of radiation. So in a sense, this guides you in how big your layers should be in your solar cell, because you don't want to make your layer too thick, because then the intensity will drop rapidly. Okay, so this is all technical issues that, and you can predict that from first principle if you want. You know, this is a nice advantage that we have at our disposal at these days. So just to give you some ideas, what you can do here is a gallium arsenide typical density functional calculation. You see attenuation coefficients on the right-hand side. We can feed that directly into a solar cell simulation and simulate efficiencies. Here, another example is a perovskite, similar thing, band structure theory with different methods. And at the bottom, you see the absorption coefficient. And you see, choosing the right method, you can very nicely reproduce actually something that you also measure. So that all confirms our theory that ab initio is an alternative to experimental work, but not a substitute. Okay. So here's a typical device simulation for a perovskite. You know, this is the hottest topic, photovoltaics, and you can see the active layer is in the middle, and you have electron transport layers and hole transport layers to assist the extraction of charge carriers in an effective way. And so I played around with some of the simulation parameters. For example, I made the layer too thick or too thin, and you see we go from 24% to 6% and 3%. So it tells you there's also a lot of experimental artwork involved when you have a highly efficient solar cell. You're messing up something and your efficiency drops quite rapidly. Okay. So so this is basically what we do on a regular basis, but we wanted to go beyond the standard device simulations, and this is a quite recent work that I want to show you, and then I'm basically at the end of my talk already. So this is, as I said, when you have plasmonic nanoparticles or up and down conversion, these are usually glass particles which are rare earth doped, and they're sitting in a surrounding glass ceramics. You see that you have features in your solar cell that make the solar cell emitting light. So it's not only absorbing light like a conventional solar cell, but with this augmentation, it's also emitting light, you know, and we have to somehow cater for it. So I showed you this weird process of extracting something from a rare earth ion and getting that population densities, blah, blah, blah. So this was to be honest, this was just to see that the thing is working, but I think you can do a lot better. And the idea is the following. So it brings us all back to Gustav Kirchhoff and Planck and and Wien and all of these guys. They showed that for a black body, and this is what I show in red, the emission coefficient and the absorption coefficient are related, okay? So if you put that into a nice theory, and that has been done by Chandrasekhar, you get this, what is called the equation of radiative transfer, which I show at the top, you know. Now, okay, the engineers probably know that technique better than the physicists, but you can use Laplace transform to solve this equation. And what you get is at the bottom, you get a modification of this Bayes law. So what you see is your intensity drops as you go further into the material, but on top of that, you have an extra current which actually increases, and that's the second part here. So you see the further you go in, the bigger that current becomes, because you have more and more of these features which are radiating and create extra photons. Yeah? And so the only problem here is this factor B omega of t, because it originally comes from black body radiation. You know? So there is some kind of revival these days of bringing black body concepts back into optics, and this is another instance. So what we are actually exploring at the moment, so the framework here is perfect. This is exactly what we need. So we plug that into our device simulations, and we have an emitting solar cell. But we don't know yet what to do with this. Is it really purely black body, or do we have to slightly modify it to have a good theory? So that's what we are working on. So all of this is a part of an upcoming book chapter. So the main author is Sandile, but you see all the usual suspects. I already mentioned Prof. Wambangi, Francis, former PhD student, Jinai. It's a 56 pages long book chapter, and I think that indicates how much we've actually done in recent years on this augmentation of solar cells. So with this, I would like to thank everybody, and I would just raise maybe one point as for the discussion here. For all of us, we're battling with load shedding and producing enough electricity on the continent. But I think there's a fundamental question here. What is the solution? Does it make sense to put our efforts into new technologies like perovskites and other systems, or would it better to take technologies which are already there and try to augment it like we do with a couple of new features, but we have a proven technology that will be robust and run for a long time? Okay, so that's it. So thanks everybody for your attention here. And I think I should leave the presentation here.
Thank you very much, Professor Quandt, for a lovely presentation that set the scene. And I love your last question. I'm not going to open this for questions, because then we're going to fall behind. So we do have a discussion right at the end. And then if you can remember your questions for then, and we'll have that discussion section. So thank you very much again.